RIP is a distance vector routing protocol that uses hop count as its only metric for path selection. What we're worried about with RIP is being the least amount of hops or the least amount of routers away to our path. Advertised routes with hop counts greater than 15 are going to be considered unreachable. If you remember from the previous chapter, that would be considered a poisoned route because 15 is the count to infinity. So if a router running RIP ever receives an update that has a metric of 16 or a hop count of 16, it knows that that network is unreachable. RIP version 1 messages are going to be broadcast every 30 seconds. It will send that message to the quad 255 address every 30 seconds, and it's going to be its entire routing table that's going to be sent. RIP version 1 is a class full routing protocol, which means it does not deal with subnet masks. It just looks at what class and assigns that subnet mask. There is no authentication with RIP version 1 either. There is a RIP version 2 that we will talk about in a future chapter that takes some of these weaknesses and addresses them, such as the broadcast messages and authentication. RIP uses two message types. The first is a request message and the second is a response. The first is a message that's sent out on startup by each RIP-enabled interface. Essentially what it's doing is requesting all neighbors to send the routing table update to that interface. The response message is then a response to that requesting router containing that routing table. So when a router boots up that's running RIP, it will send out a request message and its neighbors will respond back with its entire routing table. RIP's administrative distance is 120. Compared to all the other routing protocols that we will learn about in this class, it is the worst one. OSPF is 110, EIGRP 90, static routes are 1, and directly connecteds are 0. So if we had a choice between a RIP network, a RIP route and an OSPF route, we would choose the OSPF route. Again, the lower the administrative distance, the better the route. In the next few slides, I'm going to be referring to this topology here. We have a standard 3-router setup. We have a contiguous IP addressing scheme, the 192.168 with /24s all the way around. To enable RIP, we go into the global configuration and type router RIP. That will then change our prompt to router config-router. And what we do is we add only the directly connected networks with the network statement right here. No subnet mask is going to be needed when we type in those network statements, and again, it's only the directly connecteds. If you would ever need to disable RIP or get rid of RIP, you go to global configuration and type no router RIP. This will remove all network statements and shuts down the RIP routing process. So going back to that same topology here, if I were to configure RIP on router 1, I would type router RIP and then the network 192.168.10 because that's directly connected to its fast Ethernet, and then network 192.168.20 because that's directly connected to the serial 0/0/0. I cannot enter in any more network statements because this router does not know about those networks. We cannot broadcast those out. For router 2 has 3 directly connected networks that we enter in. We have network 192.168.20 bottom left, 192.168.30 up along the top, and 192.168.40 down along the bottom right. Notice no subnet masks again are needed. And router 3 has 2 network statements, the 40 and the 50. An easy way to figure out what your directly connected networks are that you need to type in is after you configure your interfaces, do a show IP route. And then all of your C networks, your directly connected networks, are the ones you need to type into your network statements. There are some commands that we can use to verify and debug RIP. And the first one is the show IP route. We use this command a lot of times just to view what's inside of our routing table to see if we have routes to all of our networks. When we see a RIP route inside of the routing table, it's going to have an R to denote that we learned it through RIP. We will see the administrative distance of 120, and the next number of the metric is going to be how many hops away it is. Then it's always going to say via, and that's going to be the next hop address that we would send to. We will also see the outgoing interface that we would have to send out of. So when this router got a packet that was destined for the 5.0 network, it would take that packet, send it out at serial 0/0/0 to the next hop address of 192.168.2.2. Another command we can use is the show IP protocols. This displays routing protocols configured on the router. And I'll show you a screenshot of that here in just a second. Also, there's the debug IP RIP. This will display RIP updates as they are happening in real time. Here is the show IP protocols. A lot of information here on this slide, but essentially what it shows us is the routing protocol that we're using. We can see that it's RIP. We can see when we're sending updates every 30 seconds and when the next one is due. We can see our invalids, hold down flushes. We can see who we are getting updates from, and we can see who we are sending updates to. So if I take a look here, we are sending version 1 updates out the fast Ethernet, out the serial 0, and out the serial 1. We can see that network summarization is in effect, and we'll talk about that. We can see the networks that we are sending out in our updates, the 2, the 3, and the 4. And we can see who we got information from. We got information from the 2.1 router and the 4.1 router. So show IP protocols, very good command when you're debugging RIP and trying to figure out what's going on with your updates. Here is the debug IP RIP. This will show you again in real time updates being sent and received. Here we're doing the debug IP RIP on router 2. And we can see that we received version 1 updates, RIP version 1 updates, from the 192.168.2.1 address, that's right here, on our serial 0/0/0. We can see that we're building the update entries and that we're going to be sending those out. We can see that we're sending them out to the quad 255 addresses. So this can give us an excellent idea of whether or not we're actually receiving updates or we're sending the correct ones. That's the debug IP RIP. Passive interfaces is an important concept with RIP. By default, when you enable RIP, RIP will send updates out all interfaces. Not all interfaces typically need RIP updates to be sent out. Unnecessary RIP updates impact your network. Bandwidth is going to be wasted transporting unnecessary updates because RIP updates are broadcast to switches, which will forward the updates out all ports. All devices on the LAN must process that update up to the transport layer where the receiving device will discard that update. Since it's a broadcast, they will all take a look at it but eventually discard that update. Advertising updates on a broadcast network is a security risk. RIP updates can be intercepted with packet sniffing software. Routing updates can be modified and sent back to the router, corrupting the routing table with false metrics that misdirect traffic. So if there is not a router on the other end of that interface that needs to accept RIP updates, you should disable it. Typically that's on your fast Ethernets. Typically on your serials on the other side of that serial is another router who's running RIP. In this scenario on our R2 router, if I go back to that picture here, on the R2 router, there is no reason to send a RIP update out the fast Ethernet 00. There is no router on this side to accept that RIP update. So we want to disable RIP updates from being sent out this fast Ethernet. So what I would do is I would go into my R2, type in router RIP, and then make passive interface fast Ethernet 00. And what that passive interface fast Ethernet 00 command does again is it stops RIP updates from being sent out that fast Ethernet 0/0. Boundary routers and automatic summarization. One thing that RIP will do for us is automatically summarize our networks across major network boundaries. For example, in this particular picture here, I have in the blue box, I have all 172.30 networks. I have 172.30.1 with a /24. 172.30.2 with the /24, and 172.30.3 with the /24. But then on the right hand side of the router, I switch to a 192 network. This R2 now becomes a boundary router because it forms a boundary between two major classes of networks. I have a 172.30 network over here on the left and a 192.168 network over here on the right. So what's going to happen is what R2 is going to do is R2 is going to summarize these 172.30 networks to the class that it is. So it would take all of these networks and summarize them to the 172, that should say 24, excuse me, 00 with the /16. Change that real quick here. So the 172.24.00. There are two rules that govern RIP version 1 updates in automatic summarization. The first, if a routing update in the interface on which it's received belong to the same major network, the subnet mask of the interface is applied to the network in the routing table. Let's take a look at an example with that. So R1 is going to be sending an update up to R2. R1 would include the 172.30.10 in its update and also the 172.30.20 in its update, both with the /24. And that update would be received by R2. Since R2's interface that it gets received on has the same subnet mask /24 as the updates being sent /24, it will go ahead and it will accept that custom /24. If a routing update in the interface on which it's received belongs to a different major network, the class full subnet mask of the network is going to be applied to that network in the routing update. So let's take a look at an example with that. R2 would be sending network addresses of the 172.30.3 and the 172.30.2 with the /24, and it would send that down to R3. When R3 gets that update, its subnet mask /30 and its network, the 192, is different than what is being sent, the 172 with a /24. Since it is different, we will summarize to the class, the 172.24 0.0 with the 16. So essentially, if the subnet masks match, they will accept that custom subnet mask, and if they don't, they will not. Why do we want to summarize our networks? First, we want to summarize our networks because smaller routing updates sent and received will use less bandwidth for routing updates. Instead of having to send each one of those networks individually, if I go back to this example, instead of R2 having to send each one of these 172 networks individually, we can just summarize them into one and send it out. That can use less bandwidth. In that previous example as well, R3 has a single route to that 172.30.00 network, regardless of how many subnets there are or how it's subnetted. Using a single route can result in faster lookup process in the routing table for R3. Since we have that whole entire class B network in there, we can get to all of those networks regardless of how it's subnetted. Some disadvantages of automatic summarization is that discontiguous networks will not converge. We will have routing errors. Let's take a look at this example right here. Let's say we want to get from this top router down to the 172.16.20 or to the 172.16.10. What's going to happen is when these routers down here send their updates, this router would send its update up to the top router. And we have a 172.16.20. That update's being sent to a 192.168.1.4. The /30 and the /24 do not match. So what happens is this router will summarize this network to a 172.16.00. And it's going to say the 172.16.00 with a /16 needs to be sent down and to the left. Well, this network down here, 172.16.10 with a /24, needs to get sent up to this router. The /30 of the interface that's being received on does not match our subnet mask here. So what's going to happen is this router will summarize that update to 172.16.0.0 with a /16. So now what we have is we would have a situation where part of the packets would go this way and the other packets would go this way, because this router just received 2 updates, and both of those updates said that the 172.16.0.0 network is to go down to the left, and in the second update it said the 172.16.0.0 network is to be sent down and to the right. In this particular situation, our summarization to the class of network that we are caused some problems, and it caused incorrect routing to happen. One thing that we can do with RIP is we can propagate default routes. We can use the default information originate inside of the routing RIP process. So I'd type router RIP and then default information originate. This is used to advertise default routes or the gateway of last resort through RIP. Let's take a look at this scenario down here. R3 has an internet connection. Anything that's not in R3's table would probably be sent out the internet with the IP route 0.0.0.0 statement out whatever interface this internet is connected to. Well, what if R2 wants to get to the internet? What I could do is I could type in an IP route statement at R2 saying that anything that's not in the table send out its serial 0/0/1. That information would then get sent out, it would hit R3, and then it would reach the internet. What if R1 wants to connect to the internet? Same thing, I would have to do an IP route statement that would send internet traffic up to R2, then R2 would forward it to R3, then R3 would send it to the internet. So I'd have to do a couple of extra IP route statements, those default routes, gateway of last resorts. Instead, what I could do is I could let RIP do that work for me. I already created that gateway of last resort on R3. I already created that quad 0 statement. I already created that static route with the quad 0 statements to get to the internet. Once I have that in there, all I have to do is issue the default information originate. It will take that gateway of last resort, that default route, and it will forward it to R2 and R1 in the RIP update process. That is all for this video. If you have any questions about anything, I encourage you to ask, or read over the Cisco online curriculum can maybe help clear up a few things as well. Thanks for watching.